Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my series of videos on matrices. And in particular, I'm going to walk you through an example that involves a little bit of row reduction and a connection between linear systems, matrices, and geometry. So let me share my screen with you and we can get down to business. Okay, we are given a point, 0, 1, 2, and we asked, does this point lie on the plane where the plane goes through this point and is parallel to these two vectors? Okay. So this is an example where we're given what's known as a parametric vector form of a plane, and we're given a point, and does that point lie on the plane? Now, I do have a series of videos on vectors where we discuss the form of these equations of the planes. But let me write down the particular form here. We've got a point on the plane, -5, 1, 3, and two vectors parallel to the plane. So what does the equation of a plane look like then? Okay. So the equation of the plane is just the following. So we're working in three-dimensional space here. X, Y, Z equals this, written as a column, plus, say, lambda times this first parallel vector, plus another parameter, say mu, times the second vector. And here, mu, lambda and mu are both ranging over the whole real number line. Okay, so what is this question asking you? It's asking you, does this, or the vector associated with this point, does it satisfy this equation? So you replace x with 0, y with 1, and z with 2, and you want to know, is it actually equal? Are there values of lambda and mu that makes that equation balance or hold? So let's actually write out what the question is actually asking mathematically. Are there values of lambda and mu such that 0, 1, 2 equals -5, 1, 3 plus this plus this? Okay, that's what it's asking us. All right. So this is a vector form of an equation. And what we can do is we can take this constant vector to the other side, and then we can write the whole problem as a matrix or an augmented matrix. Okay, we have, here is I guess we have the problem. We consider the problem. So let's move this to the other side. So that'll go to +5, that'll go to 0, that will go to -1. And I'll just write it down the other way. So it'll be 5, 0, -1. All right. So what is the nature of this problem? Well, it's a vector equation. We can write this as an augmented matrix. Let's write it like this, where this B vector represents the right-hand side, and the A vector just represents these two, the matrix with these two vectors written as columns. And lambda and mu are the unknowns. Okay, so now we've got our augmented matrix. Great. Now, in previous videos, we know what to do once we have this augmented matrix. We want to perform row operations on it so that we simplify the situation. We take something complicated, do some row operations, row reduce it to make it simple so we can easily answer the question about whether there are lambda and mu values such that the equation actually holds. Okay, so let me share my screen again with you and we'll see how we go. Okay, so here's our matrix. Now there's a definite algorithm for this, yeah? So the first idea is to choose a pivot entry or a pivot element. That's the one I'm going to choose because it's a 1, and I'm going to get that 1 up to the top by swapping row 3 and row 1. Now, remember, it's really important to record your operations because I make lots of mistakes and it's easy to make mistakes, okay? So let's do a switch with row 1 and row 3. All right, we've got the pivot up to the top. Great. So underneath that, we want to get everything underneath that top left-hand entry to a 0. So we want that to be 0, and we want that to be 0. So how can I do that? Well, row 2 will become row 2 plus row 1, and row 4 will become row 4 minus 4 times row 1. Okay, that'll make that a 0 and that a 0. So let's keep on going. So row 2 equals row 2 plus row 1. Now, why do you want to make 1 the pivot? Because you avoid fractions then. So it's always good to avoid fractions. Okay, so row 1 doesn't change. Okay, so row 2 plus row 1, so that'll become 0. We'll get negative 2 plus 3, which is 1, and 0 plus negative 1, that's negative 1. Row 3 minus 4, row 1. 4 minus 1, 4 minus 4 is 1. 3 minus 4 times 3, 3 minus 12, negative 9. 5 minus negative 4 times 1, 5 plus 4, 9. Okay, now we've almost finished the reduction now. You can see that I want to basically choose another, I want to work on a submatrix. That's my submatrix, and we'll row reduce that. So let's choose a pivot entry or pivot element. That's going to be it. It's 1, it's already up the top, so that's great. And I'm going to get everything underneath it to a 0. So that's going to be my new pivot. Great. And to make that a 0, I'm going to do row 3 equals row 3 plus 9 row 1. Yeah? Okay, so let's do that. So row 1 and row 2 are not going to change. So that plus that will be 0. That plus that will give you 9 plus negative 9, which is 0. Okay, this is now in a row reduced form. Okay, sorry, a row echelon form. Okay, every leading, well, all the zeros are at the bottom. The rows of zeros are at the bottom, and every leading entry in the other rows is a 1, or is 1. Well, in this case, it's 1, but it's each one's further to the right as you go down your rows. Okay, great. So now what? We've done some row reduction. What now? Well, now hopefully we can see what the nature of the solutions are. Okay, let's have a look at our row echelon form. All right, firstly, let's look at row 2. Row 2 says 1 times mu equals negative 1. Okay. We get, so mu equals negative 1. Row 1 gives us 1 times lambda plus 3 times mu equals negative 1. So, all right, so we already know that mu equals negative 1. I can take that and put it in here. So I'll get lambda minus 3 equals 1. You rearrange that, you'll get lambda equals 2. Okay, so we've answered our question now. are there values of lambda and mu such that this holds? And if that's the case, then the answer to this question is yes. Yes, there are values, okay? So we will conclude yes, our point 0, 1, 2 does lie on the given plane. Okay, so our solution is consistent. There's one and only one solution in this case. You can see all the left-hand columns are leading and the right-hand column isn't leading. So that means there's one and only one solution. Okay, great. So that's an example where you're given some sort of mathematical problem. You've got in this case, we used an augmented matrix, and we went through the process of doing row operations and putting it in a row echelon form, from which we could make some conclusion. Now, if we were given the Cartesian form of the plane, it would be much easier to solve, but we weren't. We were just given essentially the vector parametric form. Anyway, what do you think? Hopefully you've enjoyed this video. Hopefully you've learned something. Remember, the best way to get good at maths is to do it. If you have any questions, any comments, put them in the comments section. Thanks, everyone. See you. Bye.